Hi, Mr. Corsi here. This video has the complete detailed solutions to all the questions in the AQA Higher GCSE Maths Paper 3 exam from 2024. Now there's a lot of questions, but to find the particular question you might be interested in, you just need to scroll along the timeline below the video. So I hope you find these solutions are useful in your journey towards success in your GCSE exam. Well, here's question 1. And we're given first 3 patterns in a sequence. And in part A, we're asked on this grid to draw pattern 4. Let's examine what these are doing. We've got in the centre, let's take the largest one, pattern 3. We've got a 3 by 3 square in the centre with single squares tagged on round the outside each corner of that square. So a 3 by 3 and 4 squares at the corners. There's a 2 by 2 for pattern 2 with the 4 squares. There's a 1 by 1 with the 4 squares. So pattern 4 would have a 4 by 4 square at the centre with single squares tagged on. So let's draw that. So there's the result. Now let's move on to part B. And we're told in part B that this expression n squared plus 4 gives the total number of squares in pattern n. So let's check if this expression works for the patterns we've got. Now in pattern 1 we've got 1, 2, 3, 4, 5 squares. When n equals 1, 1 squared, that's 1 times 1, plus 4, 1 plus 4 is 5, so that certainly works. And when n equals 2, let's see, we've got 4 squares in the middle, plus 4 squares on the edges, on the corners, so that's 8 altogether. 2 squared plus 4, 2 times 2 is 4, plus 4 is 8. And final check, in the third one, 9 in the middle, 10, 11, 12, 13 we should get. 3 squared is 9, 3 threes are 9, plus 4, 13. So that seems to be working. Now it says work out the smallest value of n for which the number of small squares is greater than 500. So we want this number that we're getting here, the n squared plus 4, to be greater than 500. Or an equivalent statement, if we take away 4 from both sides of this inequality, would get n squared being greater than 496. Now we're dealing with square numbers here. So let's get the calculator and find out what number we need to square to get something very close to 496. In other words, what's the opposite of squaring? That'll be the square root. If we take the square root of 496, we'll see roughly where we are for the value of n. Square root of 496. Well, that's around about 22. 22 squared, let's work that out. 22 squared, that's 484. Now you can see if we put 22 in there, we would not have a number greater than 496. So let's move up one and try 23 squared. 23 squared, that's 529. And that is greater than 496. So the least value of n, so that we do get an answer bigger than 496, would be 23. So here we have question 2, and we're given a right-angled triangle, and we have to use Pythagoras' theorem to work out the value of this hypotenuse, the length of this large side opposite the right angle in this triangle. Now, let's remind ourselves what Pythagoras' theorem is all about. So here we have a right-angled triangle. There's the right angle, the two shorter sides, and then the side opposite being the hypotenuse. And this area plus this area is always equal to this area. As you can see, all these pieces in that square plus the area of the other square, they all fit exactly into this square. Now, the area of this small square would be A times A, length times breadth. That's A squared. The area of this square is B times B. That's B squared. And the area of the large square is C times C. So that's C squared. And what we just showed by rearranging these pieces was that A squared plus B squared equals C squared. So A squared plus B squared is equal to C squared. And the large square is always on the side of the hypotenuse. And it doesn't matter what the size of that triangle is, all these pieces fit precisely together so that the sum of the areas of the two small squares is equal to the large square. So that's Pythagoras' theorem. So back to the right-angled triangle in the question. Here it is. So we can now imagine the squares that are sitting on the sides of this right-angled triangle. And remember from the animation that we saw, the area of the large square, it's the hypotenuse squared, would be the sum of these two smaller areas. So x times x, x squared, this big area there, would be 24 times 24, 24 squared, plus 31 times 31, 31 squared. We've got x squared, this large square here, would be the sum of the areas of the two smaller squares. And that's Pythagoras' theorem that we're using there. So let's get the calculator onto this to find out what 24 squared plus 31 squared is. So we've got 24 squared plus 31 squared, and that gives us 1537. Now, in this equation, let's do the inverse process of squaring to get rid of this square. And the inverse process to squaring is square rooting. Now that would be this button on my calculator. So I'll be wanting to take the square root of this previous answer. So square root, and then I'll press the ANS key. That gives me that decimal. So that's x, the square root of 1537, and that gives me 39.204, and so it goes on. Now the question says give your answer as a decimal, but it doesn't say how accurate that should be. So let's just round it to 1 decimal place. We've really vandalised that number by hacking off the rest of the digits there. So we'll say what we've done. That's to 1 decimal place. So 39.2 centimetres. Well, here's question 3. And Rick is claiming that most of the flats in his 8-floor building are energy efficient, and what he does is he samples 45 of the flats from floor 1 to 5 and says, look, they're energy efficient. We have to find one reason why this sample may not be useful in testing his claim. So what he's done, he's gone floors 1, 2, 3, 4, 5, and he's sampled 45 of the flats in these first 5 floors. Now what about the last 3 floors? He hasn't sampled any flats in these. So we could say that what he's done does not represent all the flats in the building. He's ignored the top 3 floors. So we could say that it's not representative of all the flats. That would be a good reason. It would be producing possibly bias. There might be things about the top 3 floors that are not the same as the other floors. So it's not representative of all the flats. So here we have question 4. And we're told that this statement here is an identity. Now you'll notice there's 3 lines here, not the normal equals sign. We're told that's an identity, and we have to take one of these boxes. That this statement is true for all values of x, it's true for some values, and it's true for no values of x. Well, first of all, we'll find out what exactly an identity means, and we'll do that by using the first few counting values of x. X equals 1, x equals 2, x equals 3, and x equals 4. And we'll try this in various statements. The first statement would be x plus 1 equals x plus 2. So let's try x equals 1 in here. 1 plus 1, that's 2. 1 plus 2, that's 3. And certainly that statement is not true. Let's try x equals 2. 2 plus 1, 3. 2 plus 2, 4. Well, that's not so good. Let's try x equals 3. 3 plus 1, that's 4. 3 plus 2, that's 5. And again, that's not true. You can see the pattern building up. And if we work through all these statements, none of them will be true. So no values true. So that's this box down here. There's a statement where no matter what you put in for x, you'll get false statements all the time. There's no value of x which will make the statement true. Let's try another one. Let's try 2x plus 3 equals 7. And let's try x equals 1. 2 1s, that's 2 plus 3, that's 5. 5 equals 7. Well, that's not a promising start. That's not true. Let's try x equals 2. 2 2s, that's 4 plus 3. Well, there we go. 7 equals 7. That's certainly true. Let's try x equals 3. 2 3s are 6, plus 3 is 9. And there's a statement that's not true. And trying x equals 4, 2 4s are 8, plus 3, that's 11. And that certainly does not equal 7. But here we have some values that are true. So this is an example of the middle box, true for some values of x. And finally, let's try the statement 3x minus 1 equals 3x minus 3. And if we try that for x equals 1, 3 lots of 1 minus 1, that's 0. 3 lots of 0. 3 lots of 1, 3 minus 3 is 0. Well, that's true. Let's try x equals 2. 3 lots of 2 minus 1. That's 3 lots of 1. 3 lots of 2 is 6, minus 3 is 3. True again. Let's try x equals 3. 3 lots of 3 minus 1, that's 3 lots of 2, that's 6. 3 lots of 3 is 9, minus 3 is 6. And so it goes on. And you'll find that every replacement for x gives you a true statement. So all values give you true statements. And it's this last one that means this is more than just an equals here. This can be replaced by the identity sign. So if you have an identity sign in there, it means that that statement is always true no matter what value x is. That's what this one is. Always true for all values of x. So here we have question 5, and we're shown the front elevation of a cuboid, and we're asked to draw the side elevation of a cuboid, and we're told the volume of the cuboid is 42 cubic centimetres. Well, let's have a little look at building cuboids, and let's look at their front elevations and their side elevations. So let's build a cuboid. Here's a cuboid. The front elevation is a rectangle showing 3 cubes. The side elevation is just 1 cube. Now the volume of this cuboid is 3 cubes. Now let's make a cuboid that has a front elevation similar to what the question is showing us. And there's the front elevation, a 2 by 3 rectangle. The side elevation for this cuboid has a 2 by 1 rectangle. And the volume of this cuboid, if you count the cubes, there's 6 cubes. So the volume of this is 6. Let's build another layer at the back of this. Now in this cuboid, it still has the same front elevation. The side elevation is slightly longer. The volume this time, there's a couple of slices of 6 in each. There's 12 cubes altogether. So this has a volume of 12. Now let's continue with this building of another layer of 6. We've added another 6, and every time we do that, we're not altering the front elevation. It's still exactly the same. We are altering the side elevation. Now the volume of this cuboid is 1, 2, 3 lots of 6. That's 18. That's not quite what they wanted yet. Let's add another 2 layers to this. Now let's check the front elevation, still the same. Side elevation's a lot longer. What's the volume of this? Well, let's count slices of 6. 1, 2, 3, 4, 5 6s are 30. not enough. We add another 6, that's 36, and finally another 6, that would give us our volume of 42. So there's the front elevation, there's the side elevation, which has length of 7 cubes. So the breadth is 3, the height is 2, and the length is 7. And let's confirm 1, 2, 3, 4, 5, 6, 7 slices, each with 6 cubes in it. 7 6s are 42. So that's the side elevation that they're after. So let's draw that in now. Seven along, and 2 up, a rectangle. So there we are, side elevation. And this front elevation, you could call this the width, this the height, and this would be the length. Remember, cuboids have length times breadth times height, of length times width times height. For the volume, you'd multiply these together. Now the length of 7, the breadth or width of 3, and a height of 2. So the volume would be length times width times height. And 7 3s are 21, and if we double 21, we get 42. So that's a confirmation that we have the right side elevation and we've done everything correctly. Well, here's question 6, and in part A, we're told that on Monday Lars swims 50 metres in 40 seconds. 50 metres, and to swim that length it takes 40 seconds. Now we move on to Tuesday, where he gets a burst of energy and he swims 1.5 kilometres. And we assume that he swims at the same constant speed as on Monday. So the constant speed means that we can work out 1,500 metres which is what 1.5 kilometres is equal to. Remember, 1 kilometre is 1,000 metres. So 1.5 will be 1,500 metres. That's 1,500 metres. So we have to work out how long it will take him to swim 1,500 metres at the same constant speed. So what we can do is to say, well, here's 50 metres, takes him 40 seconds. Suppose it was double that. Multiplied by 200 metres would be twice that speed. If it was 5 metres he swam, that's a tenth of that, then it would be 4 seconds. It's a tenth of that. So whatever we multiply or divide one of these numbers by, we do the same to the other one. We say they are in proportion. So we can work out how long it takes them to swim 1 metre. And that would be dividing this by 50, taking a 50th of it. So we'd have to do the same to the 40 seconds. So whatever that comes to, that's the number of seconds it takes to swim 1 metre. And then we can move on to this 1,500 metres, because that would be 1,500 times what he's just swam 1 metre in this number of seconds. So we would multiply both of these numbers by 1,500. Now remember, you are allowed to use a calculator in this paper. But let's just see what we can do. Divide top and bottom by 10 and divide the top and the bottom by 5. 5 into 5 goes 1. 5 into that 15 goes 3. So we've got 4 times 300. Well, that's 1200 seconds. Now you'd easily do that in your calculator. 40 divide by 50 times 1500 and you'll get 1200 out. Now it says how many minutes does he swim for on Tuesday. Well, remember that 60 seconds gives you 1 minute. So we really need to look at 1200 and say how many 60s are there in that. And again, your calculator comes to the rescue. 1200 over 60, and that would actually give you 20. You can check that. So the answer to this question is 20 minutes. Now let's have a look at part B. And it tells us that this was a lie, what we were told, that he actually swims slower speed than he did on the Monday. Now in all this working out, we got 20 minutes by assuming he kept the same speed that he swam at on Monday, but we're now told he's swimming at a slower speed, so he would take longer. You swim slower, you take longer. Is it less than the answer? No. Is it the same? No. Is it greater? Yes, he will take longer. Instead of 20 minutes, it will be a larger number of minutes. So it's greater than the answer to part A. And it certainly is possible to say that. Well, here's question 7. And we're asked to draw the graph of y equals 1 minus a half x for values of x from -2 to 4. And here's the graph paper with the scales on it. So let's have a look first of all at this equation that we're given. Y equals 1 minus a half x. And that's a linear equation. We've got an x term and a constant. We know, therefore, that is a straight line graph. So let's start finding a couple of points on the graph. And let's do the 2 points at either end of this range. So we'll start off with x equals -2. And we'll use this formula to work out y. If a point lies on this graph, then its coordinates will satisfy this equation. So in particular, if the x-coordinate is -2, we can work out what the y-coordinate is from this formula. So y is 1 minus a half of -2. Now let's look at that. We've got 1, and think of this as negative a half times -2. That'll be positive. Negative times negative is positive, and a half of 2 is 1. So the y-coordinate is 2. So the point -2, 2 lies on this graph. X is -2, y is 2. So there is a point on the graph. Now let's go to the other end of this range of values, and we'll try x equals 4. Calculate the y value using this formula. So y equals 1 minus a half of 4 this time. And a half of 4 we know is 2, so it's 1 minus 2, that's -1. So the point 4, -1 lies on this graph. Let's join these two up. Now, we won't go outside of these 2 points because we're only told to work out the graph for values of x from -2 to 4. Now, you'd be wise at this stage to check, in case you've made a mistake here. Let's check with x equals 2. And you can see that this line that we've drawn, this graph we've drawn, passes through the point x equals 2, y equals 0, 2, 0. So we're expecting a y value of 0 from this. So let's put 2 in here, 1 minus a half times 2. And we know a half of 2 is 1, 1 minus 1 is 0. So that checks out. Another one we could do is when x is 0, y is 1. If we put 0 in here, a half of 0 is just 0, we'll end up with 1 minus 0, which is 1. So this all ties in with the graph that we've drawn. So that's our graph. So here we have question 8. And we're talking about 4 people who take part in a TV talent show. And in particular, we're focusing on Amy. And we're trying to work out her total score. Now, there's a formula down here for working out her total score. And we're told it's 4 times the mean of her marks. That's this table up here. She was awarded 6 marks. There's 6 judges. Each judge gives her a mark, probably out of 10 by the looks of it. So it's 4 times the mean of her marks plus her percentage of the phone vote. And we're given information about the phone vote in the form of this pie chart, where you're told the degrees of each of the slices of this circle. So let's try and work out, first of all, the mean of her marks. Now, remember what the mean is all about. Mean would be the sum of all the marks. That's 8 plus 9 plus 9 plus 6 plus 9 plus 10. And it's that total divided by the number of marks that there are. And remember, there were 6 of them. Eight plus 9 plus 9 plus 6 plus 9 plus 10, and that comes to 51. Be nice just to write that down. So it's that answer divided by 6, and that gives me 8.5. So that's the mean of her marks. Now, we were told that it's 4 times the mean. So let's write that down. 4 times the mean would be 4 times 8.5. So it's that answer times 4. And that gives me 34. So what's next? Well, we have to find out her percentage of the phone vote. Now, you'll notice that her slice of the cake is 162 degrees. And all the angles around this point in the centre will add up to 360 degrees. That's a complete turn around that point. So her slice of the cake is 162 degrees of 360 degrees. So her percentage would be 162 out of the total possible degrees round there, 360. That's not a percentage To turn it into a percentage, you multiply it by 1. Well, 1 in the guise of 100%. 100% is just another way of writing 1 down. So the calculation is 162 divided by 360 times 100. That gives us 45. So it's 45%. So what's our total score? Well, let's follow the recipe then. 4 times the mean of our marks, that's 34, plus our percentage of the vote, phone vote, that's 45. So we take 34 and add 45, do that in your calculator, you'll get 79. That's her total score. So here's question 9, and we've got a couple of towns. We've got town A and town B. Town A and town B. Now, what facts do we know about these towns? Well, town A, we're told, the population, we're told is 84,000. And we're told the area of town A, and it's 7 square miles. That's miles with a wee 2 up there, miles squared, square miles. And what do we know about town B? All we know about it is its population density. That's how many people are living per square kilometre. So it's 4,695 that's people per square kilometre. Now we'll notice straight away that the measurements there are different. In town A we're told its area in square miles, and we're told the population density in town B in square kilometres, how many people on average live in 1 square kilometre. So what is the population density? Well, there is a formula here that the population density is given by the total population divided by the area. And the figure we're given for town B, remember the area was in square kilometres. We're asked which town has the greatest population density. So basically we have to look at town A and work out what the population density is. But there's a problem with this area, 7 square miles. We need to convert that so that it's in square kilometres. Now they do tell us the conversion that 1 square mile is equal to 2.6 square kilometres. So that would mean that 7 square miles, that would be 7 times what we're told. 2.6, 7 times 2.6. So that's 7 times 2.6. And there we have 18.2. That's 18.2 square kilometres. So I think we're all set to work out the population density using this formula of town A, because we know its total population, that's 84,000, And we now know its area in square kilometres. It's 18.2. So there's our next calculation. So that's 84,000 divided by 18.2. There we are. It's 4,615. That will approximate it to the nearest unit. So, which town has the greatest population density? So we've got a density of 4,695 for town B, 4,615 for town A. Town B has the greater density. Town B has the greater density. Since 4,695 is greater than 4,615. So it's town B, and that calculation is the justification for the answer that we've given. Well, here's question 10. And we're rolling a biased dice. That means the chances of each of the numbers are not the same. Some numbers you're going to get more than other numbers, which is not normal on an unbiased dice. So it's a special dice, a biased dice. And we're told that the probability of rolling a 6 is 0.38. Now, let's think about what these mean. Suppose we're rolling a dice 150 times and every single one of its 6 faces has a 6 on it. Then the probability of 6 would be 1. It has to happen. And if you're rolling it 150 times, you're going to get 150 sixes. That's all there is in the dice. So you'd expect 1 times 150 sixes. Now suppose the dice had 3 6s on it and 3 5s on it. You'd expect half the time to get a 6, the other half of the time you get a 5. So the probability of a 6 in that case would be a half. And in that case you would expect a half of the 150 rolls to be 6s. In other words, you'd expect 75 6s on average. So the probability times the number of rolls will give you our answer. So if the probability of a 6 being rolled is 0.38, we roll the dice 150 times, you would expect 0.38 times 150 6s to be rolled. 0.38 times 150. That would appear to be 57. So you'd expect 57 6s. Now, is that what we're asked in the question? No. We're asked how many times you'd expect the dice not to land in a 6. So if you expect 57 6s, you'd expect the rest of them, 150 minus 57, not to be 6s. i.e., what's 150 minus 57? 150 minus that answer of 57 is 93. So it's 93. Now there is another way of doing this. Probability of a 6 is 0.38. The probability of not a 6 will be 1 minus 0.38. Remember, probabilities add up to 1 if they're absolutely certain. Now, if you roll a 6 or not a 6, that's bound to happen. So the sum of the probability of rolling a 6 and the probability of not rolling a 6 will be 1. So the probability of not 6 is 1 minus the probability of rolling a 6. So what does that come to? So 1 minus 0.38. Well, that's 0.62. So you would expect 0.62 of these 150 dice rolls to be not a 6. Well, let's work that one out. Hopefully that'll work out at the same as what we got before. Otherwise, there's something wrong with our mathematics. Goodness, 93. Well, our mathematics was okay. So 93 not 6s, that's what you'd expect. Well, here's question 11. I have to write a number in each box to make these calculations correct. So the first one, 10 divided by -2 times we don't know what, and we end up with 5. Well, we can certainly work out 10 divided by 2, positive divided by negative, that would be a negative answer, and 10 divided by 2 is 5. So we've got -5 times something gives us 5. Now let's figure out what's in here. This is negative, this is positive, and we're multiplying, so negative times negative would give us a positive answer. 5 times 1 gives us 5. That'll be -1. Now the other way of thinking about this is 10 divided by -2, as we said, is -5 times we don't know what equals 5. And we can therefore, in this equation, divide both sides by -5. That means the -5's cancel. We would get x equals positive divided by negative is -5 divided by 5 is 1. And that's what we put in the box. Let's look at the second one. We've got 1/3 times an unknown number times 6, and we get 8 pi. 8 times pi. Now, if we're multiplying three numbers, it doesn't matter which order you multiply them in. 2 times 3 times 4, that's 24. Doesn't matter if you do 6 times 4 or whether you do 2 times 12, you'll get 24 in all cases. Or we could swap them round and do 2 times 4 is 8, times the 3 in the middle. That still gives you 24. So it doesn't matter what order we do this multiplication. So we can do 1/3 times 6, and 3 into 6 goes 2. So we can replace these two boxes by the number 2, and we've still got to multiply by something to get 8 pi. So we're now thinking, what do we double to get 8 pi? Well, that'd be half of 8 pi, it's 4 pi. And again, we could put down equations, if you like. 1/3 times x times 6 is 8 pi. 1/3 of 6 is 2. 2x is 8 pi. Let's divide both sides, do the same to both sides. Divide it by 2. That cancels. We get x equals, 2 into 2 is 1, 2 into 8 is 4. We get 4 pi as before. So there we go, a negative 1 in that box, 4 pi in that box. Well, here's question 12, and we've got Haram with his pack of cards. Cards are either gold or not gold, and we're told that if he chooses a card at random, the probability that it's gold is 0.05. So the probability of gold, if he chooses it at random, 0.05. Now, since there's nothing but gold or not gold in his pack of cards, what's the probability that he gets either a gold card or a not gold card? Well, that's an absolute certainty. If he chooses, he's going to get either gold or not gold. So the probability of that happening is 1. And from this fact, you can see that the probability of choosing a card that's not gold would be 1 minus 0.05. And that's 0.95. So if we're asked to complete this tree diagram, he chooses at random a first card. Gold, we're told, is 0.05 for the probability. Not gold would be 0.95. Now, he replaces it. That's vital. He chooses a second card. Now, he's got exactly the same pack of cards as he had before. So, choosing a gold, he'll still have a probability of 0.05. Doesn't matter whether he got a gold or not gold, because he replaced whatever it was into the pack. Again, in the second card, probability of a not gold card would be what we've calculated up here, 0.95. So there's the completed tree diagram. Let's have a look at part B. We're asked, what is the probability that at least one of Haram's cards is gold? Now, if we look at this diagram, how can he get one card at least being gold? Well, he could get that happening on his first draw of a card. Now, assuming that's not happening, assuming that he didn't get a gold card, and we know that probability is 0.95, he might get that card gold on the second draw of the card. So that's all the information we need to figure out the probability that at least one of his cards is gold. He's got two possibilities, so we'd add the two possibilities together. So 0.05, and that's him got his gold card. If that doesn't happen, he can get his gold card by following the blue route here. Now, what are the chances of that happening? Well, there's a chance of 0.95 that he goes down that path, and then there's a chance of 0.05 that he chooses a gold card. So that's conditional on him going down this path. So it's a multiplication we have to do. So there's a choice between the two paths, so we add the two probabilities. On this second path, it's a multiplication because this is conditional on this happening. So there's the calculation that we need to do. 0.05 plus 0.95 times 0.05. and that gives me 0.0975. So that's the probability that he gets at least one gold card. Well, here's question 13, and we're shown a quadratic graph. It's got equation y equals f of x, and we're asked to write down the roots of the equation f of x equals 0. Well, let's look at a couple of different examples first to try and understand this situation. So here we have a quadratic graph, a parabola, and the formula is y equals x squared minus 2x. Now, if we're interested in when x squared minus 2x is equal to 0, in other words, when the y coordinate is 0, that happens when x is 0 or 2. If we put x equals 0 into this expression, 0 squared minus twice 0, we get 0 out. Also, if we put 2 into this expression, 2 squared minus 2 times 2, that again gives us 0. So if we're trying to solve the equation x squared minus 2x equals 0, and we're doing it from this graph, we'd look at where the graph crosses the x-axis. These give the roots, or the solutions, of that equation, x squared minus 2x equals 0. Now, if we change this slightly, there's another graph, different equation. Let's solve x squared minus 3x plus 2 equals 0. X equals 1 and x equals 2 are the roots or solutions of that equation. Let's try x equals 1. 1 squared is 1. Minus 3 times 1, that's 1 minus 3 is negative 2, plus 2, that indeed gives us 0. Let's try x equals 2. 2 2s are 4. Minus 3 2s, that's minus 6, that gives us negative 2. Plus 2, again we get 0. So if we're trying to solve x squared minus 3x plus 2 equals 0, from this graph, we look at where it crosses the x-axis, and that'll give us the roots or the solutions of that equation. So if we look back at the question, we're trying to solve the equation f of x equals 0. We're looking for y coordinates of 0 on this graph. One of them's there, the other one's there. So the roots of this equation, the solutions to this equation f of x equals 0, will be found where this graph crosses the x-axis. So let's have a look at that. Now there's 10 little squares between each of these integers on the x-axis. So this is 2 squares to the left of negative 2. That'll be negative 2.2. So negative 2.2 is one of the roots, and the other root 1.5, halfway between 1 and 2. Well, here's question 14, and we're shown this quadrilateral, angles A, B, Y and X, and we're told B is 45 degrees. And we're told various ratios here. We're asked to find the ratio A to Y. That's this angle up here to this angle down here. Let's start with a ratio A to B, 7 to 3. A to B, we're told, is 7 to 3. And we're told that B is 45 degrees. So this is 7 parts, and this is 3 parts. So the 3 parts will correspond to 45 degrees. So 3 parts corresponds to 45 degrees. Well, what does that make 1 part? Well, it will be a third. We'll divide both of these by 3. So 3 into 45 goes 15. So 1 part would be 15. Therefore, the 7 parts, which will get us angle A, will be 7 times that. 1 part's 15, 7 parts will be 7 times that. So it's 15 times 7. And that comes to 105. You can do that on your calculator. So we're making progress. We've discovered A is 105 degrees. So that's dealt with this. We've dealt with that. Let's have a look at this final one. X to Y, 4 parts to 1 part. X to Y, 4 parts to 1 part. So what do we know about X and Y? Well, what we do know is that we're in a quadrilateral and that the total of all the angles is 360 degrees. So we know that these two, X plus Y, must come to 360 minus the total of 105 and 45, which is 150. So if we take 150 away from 360, that gives us 210. So between these two, we've got 210 degrees. That's between these 4 parts and this 1 part, which comes to a total of 5 parts. These 5 parts are 210 degrees. So 5 parts, 210 degrees. So what's 1 part? And after all, 1 part is the size of this angle. And that's pretty good because we're trying to find the ratio A to Y. So this is what we're trying to find, A to Y. We need to find angle Y. So it corresponds to 1 part where 5 parts are 210 degrees. So 1 part would be 1/5. We divide by 5. So it's 210 divided by 5. That gives me 42 degrees. Check that in your calculator. So we've finally found what angle Y is. It's 42 degrees. So A to Y is 5 to 2, we have to show. A to Y is 105 to 42. Now if we look at this, we can divide both of these by 21. The hint is that it can be reduced to 5 to 2. So if we want 2 there, we'd need to divide by 21. And you check this in your calculator, that when you divide both of these by 21, you're going to end up with 5 to 2. Well, here we have question 15, and we're shown a straight line that passes through A, -5, 9, and C, 3, -7. And we're told that B divides AC in the ratio 1 to 3. Now that means that this part of the line would be 1 part, and this part of the line would be 3 parts. Now one of the ways of doing this is to let's look first of all at the X coordinate of A and the x-coordinate of C. And look at how the difference in the x-coordinates is divided up. Now, x-coordinate here is -5, x-coordinate here is 3. So to get from there to there, we'll have to go 5 plus another 3. That whole line there is of length 8. And it's to be divided up into one part to 3 parts, 4 parts altogether. 4 and 8 goes 2. Each part must be 2. So this must be 2. And then the 3 parts, 2 3s are 6. This must be 6. And 2 plus 6 does give us 8. The ratio is 1 to 3. So with this information, we can work out the x-coordinate of B. If we're at -5 at A, and we move 2 to the right, we'll get to -3. So the x-coordinate of B is -3. Now let's do a similar calculation for the y-coordinates. Now, that's the 2 y-coordinates from there to there. This is a height of 9. This is a height of -7. So we'll have 9 and then another 7. That's 16 in total from there to there. And again, that's divided up into 1 part and 3 parts. There's your 1 part and there's your 3 parts. Now that's 4 parts altogether, this time coming to 16. So 1 part, 4 into 16 will be 4. So this will be 4. 3 parts, 3 4s are 12. So we'll check that. 12 plus 4 is 16. Ratio 4 to 12, or 1 to 3. So that will allow us now to work out the y-coordinate of B. Let's do it from A. If we're at a height of 9 and we go down 4, we'll be at a height of 5. So the y-coordinate of B is 5. So we've finally got the coordinates of B. It's -3, 5. Now there is another way that you may have been taught to do this, and that's by taking the coordinates of A and the coordinates of C and we write the ratio down, 1 to 3, and then we use a cross to find the coordinates of B. And we get the x-coordinates by going 3 times the x-coordinate, 3 times -5, that's -15, plus 1 times the x-coordinate of C, it's 1 times 3 is 3, divided by the sum, 1 plus 3, which is 4. The y-coordinate of B, we do the same for the y-coordinates, 3 times 9, 27, 1 times -7, that's -7, divided by 1 plus 3, which is 4. So B has coordinates, -15 plus 3 is -12, divided by 4 is -3. 27 minus 7 is 20, 20 divided by 4 is 5. So that's another way of getting the point B. So let's have a look at part B. And in this part we're asked to work out the equation of the line perpendicular to AC that passes through C. So that's a line passing through C perpendicular to AC. So there it is, and we know that's a right angle. Now, how do we find the equation of this line? Well, we know a point on it. We don't know yet its gradient. Now, what I'm going to use is a formula that tells me if I know the coordinates of a point on a line and I know the gradient of that line, then I can work out its equation using this formula, y minus b equals mx minus a. We don't know the gradient of this line. We do know it's perpendicular to AC. We can use the result that a gradient of a line times the gradient of a perpendicular line to that will give us -1. So let's see if we can work out, first of all, the gradient of the line from A to C. And to do that, I'm going to look at the y difference divided by the x difference. Now, what does that mean? Well, I'll look at the y coordinates, 9 and -7, and work out their difference, 9 minus -7. I do the same for the two x coordinates, the -5 and the 3, using the same order that I used before. So -5 minus 3 for that one. So on the top line I've got 9 plus 7, which is 16. On the bottom of the fraction I've got -5 minus 3, which is -8. So I've got positive divided by negative gives me negative. 8 into 16 goes 2. So that's the gradient of the line AC. And you can check it. -2 would mean 1 along, 2 down, 1 along, 2 down, all the way along. So that makes sense. Now, perpendicular gradient, what this result means in practice is that you would change this sign to positive and invert this 2. That's 1 over 2. So check that. In this case, 1 along a half up, 1 along a half up. That looks okay for this line. So the equation we can now use, we know that it's y minus the y coordinate of the point on the line. Well, that's -7. So it's y minus -7 equals the gradient, which is a half, x minus the x coordinate of the line, the point on the line, that's 3. So let's multiply both sides by 2 after we've simplified this bit. That's y plus 7 is a half of x minus 3. So let's double both sides and we'll get 2y plus 14, and then doubling gets rid of that half and we're just left with x minus 3. And let's take away 14 from both sides. So 2y equals x minus 17. And that's a healthy way of writing that equation. The other way, I said there was another way, is to use y equals mx plus c as our formula. And in this case, we know the gradient, we've worked it out, it's a half. So y equals a half x plus c. And again, we know that 3, -7 lies on the line. So when x is 3, y is -7. So we substitute these values into the equation. Half of 3 plus c. And that should be sufficient for us to find what c is in this case. We'll get -7 equals 3 halves plus c. So if I take 3 halves away from -14 halves, I'll find out what c is. So taking 3 halves away from negative 14 halves, that's what negative 7 is negative 17 halves. So the equation we're after is y equals a half x minus 17 over 2. And if we double both sides, we get what we got before. Double half x and double negative 17 over 2. The negative 2 disappears, and that's what we had before. Well, here's question 16. We have Jing rolling a fair six-sided dice 72 times. Now this frequency table shows us results for these 72 rolls. He rolls a 1 16 times, a 2 11 times, and so on. Now we're asked to compare the relative frequency of him rolling a 5, that's the 14 that he got, and compare it to the theoretical probability. Now let's tackle the theoretical probability because it's a fair six-sided dice. Each of these numbers has an equal chance of being rolled. So the probability of rolling a 5 in particular would be 1 chance out of 6. There are 6 different outcomes. And what about the relative frequency? What actually happened? So the relative frequency of a 5, he rolled 14 of them, and he did the rolls 72 times. So 14 out of 72 rolls of the dice, he got a 5. And we're asked to compare this relative frequency with this theoretical probability. Is 14 over 72 greater than 1/6? Now it's difficult to compare fractions like this. Let's turn them into decimals. So 1/6, 0.1, and the 6 repeats. (14) divided by 72, that's 0.19, and the 4 repeats. So if we round them off to 2 decimal places, this is 0.17 and this is 0.19, and that's to 2 decimal places. And you can see that the 0.19 is greater than 1.7. The relative frequency is greater than the theoretical probability. So is the relative frequency of rolling a 5 greater? Yes, it is. Well, here's question 17a, and we're told that a and b are different prime numbers and that a cubed times b squared equals 200. Well, we're going to have to find how 200 is constructed from prime numbers. Now there's all sorts of ways this factor tree can be built. Suppose we do it as a 20 times 10. 20 would be what, 4 times 5? 4's 2 times 2. Now we've reached the end of this branch because both of these are prime numbers. This branch is finished because 5 is a prime number. This one's not. We can write 10 as 2 times 5. But we're now finished because 2 and 5 are both prime numbers. Now this factor tree tells us that 200 can be written, and we look at the ends of all the branches, 2 times 2 times 2 times 5 times 5. In other words, it's 2 cubed times 5 squared. Now, if we compare the expression that they give us, a cubed times b squared, well, we can see that a is 2 and b is 5. So work out the value of a to the 4 times b. So a to the 4 times b will be 2 to the power 4 times 5. Now, 4 2's multiplied together, 2, 4, 8, that's 16. And 16 times 5, do that in your calculator, it turns out to be 80. So there's the answer to part A. Now let's move on to part B, and we're told that C and D are different prime numbers, and we have to circle the equation for which this expression, c to the power 4 times d squared times e, is a cube number. Now let's think about cube numbers. If we have a prime number to the power 3, that's a cube. Suppose we have p times q, and we cube that, then that's a cube number. That's p cubed times q cubed. Suppose we have p squared. Well, that's not a cube number. But if we raise it to the power 3, it will be a cube. And p squared times p squared times p squared will be p to the power 6. Another example, suppose we have p squared times q. And if we cube that, then we've got a cube. And when we multiply all these out, we'll get p to the power 6 times q to the power 3. Now you can see for cubes, we need the powers to be 3's or 6's, or maybe 9's or 12's and so on. Now let's have a look at what we've got. We've got c to the power 4 and d to the power 2. If we move this up to a power 6, in other words multiply it by c squared, that would be useful. And if we move this power 2 up to a power 3, so multiply it by d. So what do we get? We get c to the power 6 times d to the power 3, and I think that is a cube number, because if we write it as c squared d cubed, that'll give us our c to the power 6 and our d cubed. Let's just check that. C squared d times c squared d times c squared d. There's c squared times c squared times c squared will give us our c to the power 6, and d times d times d gives us d cubed, and that is a cube number. So what are we making e? We're making it c squared d, which is that choice. Well, here's question 18, and we're given this triangle, various measurements there, and we're asked to find angle x using the sine rule, showing it's approximately 64 degrees. Now in your formula sheet, you do get given the sine rule, but you have to know exactly what these letters mean. The small letters stand for the lengths of sides, and the large capital letters stand for the size of the angles. So this first bit says, let's take length A and divide it by the sine of the angle opposite. And that turns out to be the same as the length of side B divided by the sine of angle B, and length C divided by the sine of angle C, which is opposite. So that's what this means. All these fractions are equal. So in this case, we would have 11 over sine x being equal to 7 over sine 35. Now, I can do a bit of rearranging here. If I multiply both sides by sine 35 and then multiply both sides by sine x, I'm going to end up with no fractions. So I'll get 11 sine 35 equals 7 sine x. And my final move would be to divide both sides by 7 to get sine x on its own. So that's 11 sine 35 over 7. Now we need to bring on the calculator to complete this. And could you make sure before you do trig in degrees that this is reading degrees and that you don't have a rad on your screen or a grad on your screen. These are like different languages. Your calculator has to speak degrees, otherwise you're going to get all the wrong answers. So we need to put in 11 sine 35 over 7. So it's 11 times the sine of 35 and divide that by 7. So there's our answer, 0.9013. 0.9013 and so on. Now, at this stage, we're wanting to get rid of the sine. In effect, we're saying what angle, we want just this angle, what angle has a sine of 0.9013? So the opposite of sine is sine to the minus 1. On your calculator, you'll find that as an option on your sine button just above it. What angle has a sine of? And that's accessed by using this shift key. So we need to do sine to the minus 1 to get rid of this sine so that you'll get x. And we do sine to the minus 1 of this answer. So shift key, what is the angle whose sine is this number? And the answer to that, 64.33 and so on. So x equals 64.33, etc. And that is approximately 64 degrees to the nearest degree. We're chopping a 3 off. And in part B, we're given another triangle, and we're saying that Anna thinks that W must be 64 degrees to the nearest degree. She says this is the same triangle as this, because it's got two sides the same and it's got the angle the same. And let's not do any more calculations, just say, is she correct in this? And I would say no, because look, this 35 degree lies between these two angles. Here, it doesn't lie between these two angles. 35 degrees in this angle has 7 opposite it. In this triangle, the 7 is not opposite the 35 degrees. So we'd say something like that. In this triangle, 7 is not opposite 35 degrees. So they can't be the same triangle. So no, she's not correct. Here's question 19. And in part A, we're asked to work out the values of f, g, and in brackets we've got a 6. Now f and g are defined to be functions with these given formula. So the question we're asking is, what does f, g, with a 6 in brackets, what does this mean? Well, it means that we start with a 6, and g is right next to the 6. So we apply g, that function, with this formula, to 6. And we end up with a new number. Now this new number is right next to the f. So that tells us that we next have to apply the function f with this formula to whatever number this is. So inside f goes the number g of 6. Well, that's what we're supposed to be doing. So let's try and work out g of 6. So we go to the formula for g and we'll say, okay, let's replace x by 6. So it's 4 times 6 minus 7. So that's 24 minus 7, that's 17. So here we've reached the number 17, and we've now to apply f to that. So 17 goes into this function f, which has a formula x minus 3. So whatever goes in here, you take 3 from it. So f of 17 will be 17 minus 3, and that's 14. Let's have a look at part B. Here we're using the same two functions, and on the left hand side we've got f of x, and then we're squaring that, and that's equal to g of x. So let's look at what f of x is. F of x is x minus 3. So we're taking x minus 3 and we're squaring it. And what do we know about g of x? It's 4x minus 7. So we're sitting looking at an equation with x in it. First of all, let's tackle the x minus 3 squared. Now remember, that means x minus 3 times x minus 3. And depending how you were taught to expand these things, well, there's two basic ways that you can do this. First outside, inside, last. The first term in each bracket, x times x is x squared. The outside two terms, x times negative 3, that's negative 3x. And then the inside two, negative 3 times x. And then the last term in each bracket, negative 3 times negative 3, is plus 9. So there's x squared minus 6x plus 9. The other way you might have been taught to do this is to set the thing out in a table. So you've got a place for all of these four products, x times x, x times the negative 3 is negative 3x, and negative 3 times x, and then negative 3 times negative 3 is positive 9. So we get the x squared, couple of negative 3x's and a 9. So on the left hand side, however you did this, x squared minus 6x plus 9. Now this is a quadratic equation. It's got an x squared term, it's got x terms, and it's got numbers. And quadratic equations, we always try and solve this by setting everything on the left equal to 0. So in particular in this equation, we would try and get rid of that 4x. We'd take 4x from both sides, keeps the equation balanced. And then to get rid of this minus 7, we'd do the opposite, we'd add 7. So these are the actions we're going to take to each side of that equation. So we've got an x squared, a negative 6x, and another negative 4x be negative 10x. 9 plus 7, 16. And everything on the right hand side has vanished. And what we do now to proceed is to factorise. So the first terms. I'm thinking about FOIL again. Firsts give us x squared, so there is no choice. It's x times x. Now for the 16, the lasts, 4 4s are 16, or 2 8s. Now 2 and 8, interesting, because we're trying to get a 10 in the middle. So let's try a 2 times an 8. Now, the outside 2 gives us x times 8. The inside 2 give us 2x. And how do we get a negative 10x from these? Negative 8x and another negative 2x. So they're both terms are negative. That ties up with this positive 16. Negative 2 times negative 8 does give you 16. If you're into the table method of doing this, you would set up x squared as an x and an x. 16 you could try 4 4, or you can try the 2 and the 8. You get your x squared. We're forgetting about negatives and positives at this stage of the game. 2 8 is 16. And again, you're now looking at how do I get negative 10x? Well, it's negative 8 and another negative 2. So that would imply this is negative and this is negative, and that works out to give you a positive 16. So whatever way you do it, there is the result. So we've got a couple of brackets multiplied together equals 0. Now if you multiply two things and you get 0, one or other of them is 0. So either x minus 2 is 0 or x minus 8 is 0. One or other of these two expressions gives you 0. So add 2 to both sides here, add 2 to both sides, add 8 to both sides here. So x equals 2 or 8. That's your answer. So here we have question 20, and this is to do with direct and inverse proportion. We're told that P is directly proportional to Q. That's what this little symbol means. P directly proportional to Q. So what does that mean? Well, it means that we can find P by multiplying Q by some constant K. Now we're told a fact about values. We're told when P equals 8, Q is equal to 2. So let's use these values to find out what this constant K is. So 8 will be K times 2. 2 times 4 is 8. K equals 4. So we now know the relationship between P and Q. P is equal to 4 times Q. So let's move on to the second fact we're told. R is inversely proportional to Q squared. R is inversely proportional, so that means we put 1 over Q squared. It's not a direct proportion, it's an inverse proportion. So that's how we'd write that with this proportional sign. And it means the same as we had before. R is some constant times 1 over Q squared. So R equals some constant times 1 over Q squared. And it's probably better to write that as C on the top over Q squared. Let's do that. Now the reason I'm using a different letter instead of K is because it's unlikely that the value of this constant is the same as the 4 that we got in part 1. So r is some constant over q squared, and again we're given values. So let's write that down. So when r equals 10, we know that q is equal to 3. So just like we shoved in the values in the previous example, we'll do that here. 10 is equal to this constant that we're trying to find over 3 squared. Well, 3 squared is 9. Multiplying both sides by 9 will get c being 90. So we finally found the relationship between r and q, because we now know this constant is 90. So we can write that relationship down. R equals 90 over q squared. Okay, so what's the question now asking us? It says we have to work out the value of r when p is 0.5. Okay, so when p equals 0.5, now we're armed with a couple of formula now. We have to find r. Well, first of all, we can put p into this formula. We'll get 0.5 is 4 times q. So how do we find q? We'll divide both sides by 4. So q equals 0.5 divided by 4. 0.5 divided by 4. 0.125. So we found q. Well, if we put this value of q into the second formula, we're going to find r, which is what we're after. So r is now equal to 90 over 0.125 squared. So 90 divided by that answer squared. I have a squared button. You will also have a squared button in your calculator. 5,760. Well, here we have question 21, and they've given us a cylinder and a sphere. They've been kind enough to give us the volume of a sphere formula. We're supposed to know the volume of the cylinder formula. And they're telling us the volume of the cylinder and the volume of the sphere are equal. We have to work out the ratio of r to h, radius of the base to its height. So let's write the first bit of information down. The volume of the cylinder equals the volume of the sphere. So what can we say from that? Well, the volume of the cylinder, this is a prism with a circular base, and the volume of a prism is always the area of the base times its length or times its height. So it would be the area of the circle of radius r times that height. So it's pi r squared times h. And the volume of the sphere, well, we're told that it's 4/3 pi r cubed. Now it's interesting that this equation, we've got a product of things. We're multiplying all these terms on the left, we're multiplying all these terms on the right. Well, that would imply we could cancel terms on both sides, divide both sides by the same thing. So let's look in more detail at what numbers we're multiplying on the left and on the right. So pi times r, that's pi r squared times h. So these four numbers being multiplied. On the right we've got this number 4/3. There's a factor of a pi, we're multiplying by pi, and then we've got 3 r's multiplied together. Now if we're dividing the left hand side and the right hand side by a number to cancel them out, we can do that with the pi. Pi into pi goes 1. There's pi into pi goes 1. So we've divided both sides by pi, so the equal sign will still be valid. We've balanced the equation here. And we can do that for r, divide left hand side by r, divide the right hand side by r. R into r goes 1, r into r goes 1. There's another factor of r that we've cancelled from both sides. Now, I think that process has been completed. On the left hand side, 1 times 1 times 1 times h. On the right hand side, 4/3 times 1 times 1 times 1 times r. 4/3 of r. So that's considerably simpler than what we started with. So the ratio of r to h, that would be involving the lengths of r and h. We're comparing the length of the radius to the length of the height. So let's draw a line that represents the radius. Now, a line to represent the length of the height, this tells us it would be 4/3 the length of this line. Now 4/3 is 1 1/3, so it's going to be longer than this line by 1/3 of this line. So if we divide this line up into thirds, then a line representing the height would be that length plus 1/3 of that length. So there's your original length of the radius plus 1/3 of that. That line represents the length of the height. So the ratio of r to h, 3 parts to 4 parts. R to h has a ratio 3 to 4. Well, let's look at part B now. And we're told that a different cylinder has a radius that's 3 times this radius and a height that's twice this height. And we're asked how many times bigger is the volume of this cylinder than the volume of C. So the old volume, remember it was pi r squared h. So let's look at the new volume. Now it's going to be pi r squared times h, but of course r has changed. We're told that r is now 3r, so instead of r squared, it's going to be 3r squared. And instead of times the height, it's going to be times 2h. Okay, let's see if we can do something with this. Pi times, now 3r times 3r would be 9r squared. And we have 2h. Now 9 times 2 is 18. Pi r squared h. And what do we know about pi r squared h? Well, that's just the volume of the old cylinder. So we've got 18 times the volume of the old cylinder. How many times bigger is the volume of this new cylinder compared to the volume of the old cylinder? Well, the volume of the new cylinder is 18 times the volume of the old cylinder. So the answer is 18 times. Well, here's question 22, and we've got Fatima choosing a 4-digit code. So she's making up a code consisting of 4 digits, and each digit is a whole number from 0 to 9. So the things she can choose: 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. That's all she's got to choose from. So what's her decision? She decides that all her digits will be odd numbers. So we can wipe out the even digits from this, and that leaves her with a choice 1, 3, 5, 7 or 9. So that's what she's now got to choose from. No digits will be repeated. How many different codes can she make? Well, let's start off. She's got to choose something for her first digit, and her choices, there's 5 different choices she can make. Now, suppose she chooses one of these. Remember, she said that she didn't want to repeat digits, so she doesn't have 5 choices for this one, because she's chosen one of these, so she only has 4 left. If she has chosen a 5 for the first digit, she can only choose from the 1, 3, 7 or 9. So she's now got 4 choices. And you'll notice so far that for each choice she makes for the first digit, suppose she chooses a 1, for that choice she has 4 more choices for the second digit, and if she chose a 3, she's got 4 choices for the second digit. If she chose a 5, she's got 4 choices for the second digit. If she chose a 7 for the first digit, 4 choices for the second digit. If she chose a 9 for the first digit, 4 choices for the second digit. Altogether, 5 times 4, there's 20 different ways she could have done all that. So we're multiplying these choices to get the total number of choices. So once she's chosen the first 2, she's now only got 3 digits left. So for each one of these 20 choices for the first 2 digits, she can choose the next digit in 3 different ways. So again, it's a multiplication. And you can see the pattern here. For the last digit, she's now got 2 choices left. And again, we'll be multiplying to get the total number of choices. So the total choices she could make for this 4-digit code is 5 times 4 times 3 times 2. And we can work that out by saying 5 times 2 at the end is 10, 4 times 3 in the middle is 12, 10 times 12 is 120. So she has 120 choices for different codes. Well, here's question 23, and we're told that a quadrilateral ABCD is reflected in edge BC, and we're asked how many of the vertices are invariant. Well, let's draw a quadrilateral. So there's one side. It's another side. Just doing a random quadrilateral. There's another side. And final side and we'll call it A, B, C, D. And they're saying this is reflected in edge BC. So this edge, the last edge that we drew, is the mirror line. Let's do a dotted line down there. So along that dotted line, we're going to put a mirror, and we have to reflect this quadrilateral ABCD in that mirror. So let's do that. So here's the image of that quadrilateral reflected in the edge BC. Now they're asking us how many of the vertices are invariant. Invariant means they don't move after you've done that reflection. Well, there are two of them. The point B doesn't move, and the point C doesn't move. D does. It moves over to here. We'll call that D dashed. It's the image of D in the mirror. And A moves away over here. We'll call that A dashed. So C and B do not move. They're invariant when they're reflected in that mirror line. So the answer to the question is 2. Well, here's the last question, question 24. And we're asked to take this quadratic expression and write it in this special form. Sometimes it's called completing the square. So we start off with 2x squared minus 12x plus 7. And the form we're trying to write it in is some number times something squared, and a number tagged on at the end. So let's start out by looking at the B. There's a number tagged on at the end. So let's just look at the first two terms, and we'll notice that there's a 2 as a common factor there, which we could take outside brackets. So 2x squared minus 12x would be double x squared minus 6x. So there's our first move. Now, is this x squared minus 6x? It's supposed to be something squared. X squared minus 6x is supposed to be something squared. Two terms that are identical. Now, how would we do that? Well, x and an x certainly give us that x squared. And this is the problem. The outside 2 multiplied and the inside 2 multiplied are supposed to give us this negative 6x. That's where the x term comes from. And since these brackets are identical, then they each must contribute the same amount to getting a negative 6x. So they each must contribute a half of this negative 6x. In other words, they would have to be negative 3. There's your negative 3x, and another negative 3x would give you that negative 6x. Now, unfortunately, this expression is not the same as this. Because when you multiply out x minus 3 times x minus 3, whether you do it by first outside, inside, last, or by the table, here's your x squared, your minus 3x, but we've got an awkward term, a constant 9. We've got our x squared, we've got our minus 6x, but we've suddenly introduced a 9. There's a 9 here when we multiply it out that we didn't want. Well, if we've got a 9 and we don't want it, let's just take it away. So certainly x minus 3 times x minus 3 will give you all of this, and we've taken away the 9, so we do get x squared minus 6x. So that can be written as x minus 3 squared minus 9. So that this in here, Now, we'll get confused with all the brackets we're going to have, but let's put this inside square brackets. All we're doing at this stage is replacing x squared minus 6x by this. X minus 3 all squared minus 9. Because we've worked out here that that is identical to x squared minus 6x. Well, are we getting anywhere? Let's multiply out the big square brackets. So it's a couple of x minus 3 squareds and a couple of negative 9, so it's minus 18. And this plus 7 doesn't come under the influence of that 2 times, it's just tagged on at the end. Now we are getting somewhere here, it's beginning to look promising. So we get 2 lots of x minus 3 all squared, and then negative 18 plus 7 would be negative 11. And let's compare it. The d at the front is a 2. X plus e, well that's e is there, which is negative 3, and plus f, well that's negative 11, adding negative 11. So we've got it in the form that's been asked for. So we have 2 lots of x minus 3 all squared minus 11. So that's Mr. Corsi signing out, and I hope you enjoyed the video.